All right. Hello, class. Psychology 135, Cognitive Psychology. This is Dr. Palmer recording my lecture from my hotel room in Philadelphia at the Human Factors Conference. So we left off last time talking about cognitive maps and the ideas of route maps and survey maps and how those correspond to egocentric and allocentric representations. And we only have maybe one more thing to do here um, last lecture for chapter 4. And that's to talk about how you think in your mind about verbal information. We're talking a lot about visual information, so it'd be useful to think about how you are mentally imagining verbal information. And when you're given a list of items to remember, and this is a kind of list that's stored in your short-term memory. It's not really permanently stored. It's something that you're just using for the moment. You tend to remember those list of words by repeating them to yourself in serial order. So if I tell you that you're heading into the store and I say, okay, don't forget to get milk, bread, eggs, cheese, salad, and you have to remember that before you have a chance to write it down. You might be looking for a piece of paper and you'll say to yourself, milk, bread, eggs, cheese, salad, milk, bread, eggs, cheese, salad. You'll repeat them to yourself in that particular order. So that's what we mean by saying that lists are remembered serially. The second aspect of verbal lists that you imagine in your mind is that they are acoustic. They're acoustically encoded. And what that means is that they have the same time it takes to pronounce in your mind as they do out loud. We recognize the acoustic and or phonological properties of the things we're saying in our minds. So maybe a simple example of this is you could be reading a book and the author uses a very nice turn of phrase. Or you could read a poem and appreciate that it rhymes. How is it that you know that it rhymes unless you're hearing the way that those words sound in your mind as you read it? So that's the idea of acoustically encoded. And the second thing that's really interesting about acoustic encoding is that words that take longer to pronounce out loud also take longer to rehearse in your mind. So if you have to remember a 4-syllable word, it's going to, a list of 4-syllable words, it will take you longer to repeat that list of 4-syllable words than it would take for you to repeat a list of 1-syllable words. The 1-syllable words can be rehearsed quickly in your mind, where the 4-syllable words take much longer to rehearse. And that ends up having certain consequences that we'll talk about when we get to the chapter talking about memory, chapter 6 and 7. Those consequences are if things take longer for you to repeat, so you're going through your list in serial order, if it takes you longer to get through that list and get back to the beginning, then there's a chance you might lose some items. So the longer you have sort of a window of time that you need to refresh these things in your short-term memory. And if you takes too long for you to get back through the list to repeat it, then you might lose some of those words. The serial lists also tend to have a hierarchical organization. You can impose structure on your serial lists. So going back again to the grocery example, you might think, okay, I need to go get, for instance, breakfast stuff. I might have that category in my head. And then I think, all right, so within breakfast, I need, cereal, milk, eggs. I need lunch stuff. I need to go get a slice of bread, a loaf of bread that I can make sandwiches with for school, or whatever it is. So you can have this kind of categories and subcategories in your list. And this serial list information, the kind of verbal information, this verbal imagery, so to speak, makes up an important part of Baddeley's theory of working memory. So again, we're going to talk about this in more detail when we get to chapter 6. But I want to bring it up now and kind of plant some seeds, get you thinking about this working memory idea. So Short-term memory and working memory are very nearly synonymous. They mean just about the same thing. And except there's an implication with working memory that you're not just holding on to items in your memory, for instance, repeating a list like milk, bread, eggs, cheese. Instead, it's the idea that you're manipulating that list. That's the working part. So if I said, okay, take the words work, milk, bread, egg, cheese, and put them in alphabetical order, then you would think, okay, bread, cheese, eggs, milk. And that manipulation is the distinction. That's what makes it working memory, because you're manipulating the symbols, not just passively repeating them. So Baddeley's got this theory of working memory, and it has 4 different components. The first component is the central executive. This is the strategic or decision-making part of your working memory. It's the component that's in charge and farms out subtasks to the subsystems. Those 3 subsystems are the visual spatial sketchpad, which if you're doing mental imagery, that is where that mental imagery is going on in this visual spatial sketchpad. And you should understand now why it's called visual spatial, because in the last lecture, we talked about the dorsal and the ventral pathway in terms of visual processing. You have 2 distinct pathways. One is visual, goes to the temporal lobe, and the other is more spatial, it goes to the parietal lobe. So the visual spatial sketchpad is one component. That's where you hold mental imagery in mind. That's where, for instance, if you were in a store and you were looking at a new piece of furniture and you call up a mental image and you think about what will that furniture look like in my room, or if you're in a room and you're back home and you're looking in your room and you remember that piece of furniture that you saw in the store and you think, would that fit in this corner between my 2 dressers? You're performing a sort of spatial task where you're mentally imagining that piece of furniture and how it would look in your room and what spatial extent it would have. So that's the visual spatial. A visual task would be more like you're at the furniture store looking at a piece of furniture and thinking, would it fit with the decor of your room? Would it match the color scheme, right? That's the visual characteristics. So that's a visual spatial sketchpad. The episodic buffer is a portion of working memory in which you organize sequences of events. So for instance, somebody might tell you, hey, how was the party last night? Oh, it was great. Bob was there, but before Bob, Charlie showed up, and actually Mary came early to help me set up. So you should realize after talking to that person that the order of the people showing up to the party was Mary, Charlie, Bob. But in fact, in the sentence, they told you about Bob, then Charlie, then Mary. So you've got to keep track the order, you got to separate the order that you heard the events and the order in which they actually happened. So that's an episodic buffer. And you use your episodic buffer. I'll give you 2 quick examples. One might be if you're going to tell a joke. So first thing you do is you think about the punchline of the joke. And then you remember, okay, that's the punchline. And then you have to think about what's the setup and what elements of the joke do I need to tell first, second, third in order to get to that punchline so that the punchline works. A second example of when you would use your episodic buffer, think about a doctor who is interviewing a patient. The patient comes in complaining of something, and the doctor needs to take a background history from that patient. And so the doctor, she might ask, when did your symptoms start? What kind of symptoms are you having? And the patient's story may come out in a very jumbled order. They may talk about what's happening now, then they may jump back in time and talk about what happened a couple weeks ago, and then they may, skip forward. Will this injury or this illness interfere with this something I have going on at work next week? And so their story can be all over the place. And you as the doctor need to come up with a narrative for the story. And that involves collecting all that information, thinking about the order that you should present it, and then getting it into the proper order. So briefly, that's the episodic buffer. And then now the reason I'm bringing up Baddeley's theory of working memory is because of the phonological loop, which is being shown right here on the right. So in the phonological loop, first of all, phonological because there's a sound element to it, as we were discussing a moment ago, and loop because you tend to repeat a list of words to yourself and then go back to the beginning and repeat it again. So you kind of rattle through the list, go back to the beginning. That's the loop part. So the phonological loop is your verbal store in your working memory, and it's how you hang on to and think about verbal information and how you manipulate those sorts of things. So we're talking about the phonological loop, and we're talking about serial lists of verbal information, and it's in the chapter on mental imagery. But I wanted to provide for you a little context in terms of Batterley's theory of working memory. So you heard this before, and it doesn't sound so foreign when we talk about it in a couple of weeks. All right, so that's chapter 4. This also means that I need to post a chapter 4 quiz, and so I will do that. I'm writing myself a note. So your chapter 4 quiz is going to get posted, and that is the end of chapter 4. So now let's talk about chapter. This is about representation of knowledge, and I suspect that I won't get through the whole thing in this first lecture. I will get us another lecture, so we've got for the week. Have 2 lectures if I were in town. So, okay, chapter 5, representation of knowledge. What we mean by that is, maybe this is a different way to kind of put it or to pose the problem. You know a lot of stuff. You know a ton of just random facts and information. And those things are stored in your mind somehow, in some format. And so the question we're asking in this chapter is, what is the format of how all this knowledge is stored in your mind? What can we say from the perspective of cognitive psychology about what you know and how it's organized? So that's what we mean by representation of knowledge. And importantly, we need to think about how not just the facts that you know in your memory, like tigers have stripes and zebras have stripes, and etc. But you want to think about how they're related. So for instance, tigers have stripes. That's 2 concepts. One's the concept of stripedness. The other's the concept of tiger. And you can imagine those 2 as being sort of individual concepts that have a link together. So when I think about tigers, I also have a link to thinking about stripes. And then that link for stripes, that concept of stripes, also has a link to zebras. And zebras are a separate concept from tiger, but both tigers and zebras share the idea of stripes. So somehow there's some relation between those 3 things. And how should we be thinking about information like that and the interrelations between pieces of information as they're stored in your mind? So first, let's talk about how people get information into their network, into their knowledge structures. And the first thing to understand is that people are not recording the verbatim information that they see. They instead are recording the meaning. They are keeping track of the information that's being presented more than they're keeping track of the precise words that were used to communicate that information. So let's look at a pretty classic study here that illustrates this. So in the first condition, in the verbal condition, we've got 4 sentences here that are very, very similar, but they differ in some very subtle but important ways. So the first sentence here says, when you score your results, do nothing to correct your answers, but mark carefully those answers which are wrong. The sentence is almost exactly the same. When you score your results, do nothing to correct your answers, but carefully mark those answers which are wrong. So there's a word inversion here. Difference between mark carefully and carefully mark. And the thing that's interesting is we flipped these 2 words, mark carefully or carefully mark, but it doesn't really change the meaning of the sentence, right? It's exactly the same thing if I say, mark carefully those answers or carefully mark those answers. It doesn't really change the meaning, but it's still a word inversion. Okay, now let's look at those second two sentences. Actually, the comparison is really between sentence one and sentence three, and sentence two and sentence four. But let's look at one. So when you score your results, do nothing to correct your answers, but mark carefully those answers which are wrong. Sentence three, when you score your results, do nothing to your correct answers. So instead of do nothing to correct your answers, now we're saying do nothing to your correct answers. So again, we've just switched the order of words, your correct and correct your, but now we have a meaning switch. So the first one says, do nothing to correct your answers. I'm telling you to inhibit an activity. This one's saying, do nothing to your correct answers. I'm also telling you to inhibit an activity, but the first activity is to regarding your wrong answers. So do nothing to correct your answers. I'm talking about your wrong answers. But when you score your results, do nothing to your correct answers in the third sentence. Now I'm talking about your correct answers. All right, so there's a meaning switch. In this case, in the first sentence, I'm telling you don't do anything to your wrong answers. In the third sentence, I'm telling you don't do anything to your right answers. All right, and if you look at sentences 2 and 4, it's the exact same comparison, correct your answers versus your correct answers, except these two have carefully mark instead of mark carefully, right? So here's basically a 2 by 2. We're going to flip words to correct your answers or your correct answers, and we're going to flip words between mark carefully and carefully mark. And the question is which, when people read this sentence and then later on were shown one of these sentences and said, which one did you read? Okay, they tended not to notice if you switched mark carefully with carefully mark. That wasn't a distinction that people were able to remember. It just didn't occur to them. They were very bad at noticing that distinction. However, if you switch it from do nothing to correct your answers and you change it to do nothing to your correct answers, people tended to notice that switch. So this is a nice experiment because all you've done is just flip the order of two words. And what the experimenters have demonstrated is it's not just word order that people are noticing, it's word order that has a consequence. It's word order that changes the semantic message of the sentence, that changes its meaning. So going to the previous slide, under verbal memory, if you have a different sentence that has the same meaning, like mark carefully or carefully mark, people tend not to notice. But if you have a different sentence with a different meaning, like your correct answers or correct your answers, then people definitely notice. All right, so that's the first idea. You're not remembering all the details of a message unless those details happen to change the meaning of the message. Then it's clear. All right, so you're remembering the meaning of the message more than the details of the message. That's not just true for verbal information, it's also true for visual information. So let me show you this study. I went and found the original stimuli used in the study, which are admittedly pretty bad. The book has redrawn versions of them, which are better. So, but this will work. So what participants were shown was this picture in the upper left. Okay, you have a woman who's standing in front of a map, and there's a young boy who's in what looks like a desk. So it seems to be a school scene. And people were shown this version A in the upper left, and then it was taken away. And then they were shown one of two pictures, either this one in the upper right or the one at the bottom. And people were asked, is it the same picture or not? All right. The correct answer in both cases is no, they're not the same picture. The difference in this one in the upper right is the woman's dress changed. Okay, the pattern of her dress from pleats to polka dots. In the bottom picture, what changed is the woman has the same dress, you'll notice, but the picture behind her. So this one is a picture of a map. Now this is a picture of some drawing of some sort. So people tended to be much better at noticing the change when the map changed into a drawing than when the dress changed into a polka dotted dress. And the reason here is that this changes the class that was being taught as opposed to changing her fashion. And people seem to be better at noticing that the content of the course had changed than they were that the woman's fashion style had changed. So again, this is goes down to the idea of visual memory. Um, Different pictures, but if they have the same meaning, the change of the dress didn't change the meaning of the gist of the scene, then that was not noticed. But if the picture changed the gist of the scene by changing the topic in school that the woman was teaching, then that tended to be something that people noticed. So this is all in support of the idea that people remember the meaning of a communication, whether it's verbal or pictorial, more than they remember the particular style of the communication. And I want to introduce some terminology here. Sometimes we talk about tokens and types. So a token is a particular individual or a particular representative of a type. A type refers to a whole category. So for instance, a type might be a bird, and a token would be a robin or a cardinal or a blue jay or even an ostrich or a penguin. Those are all different types of birds. I'm sorry, different tokens, but a type is the entire category. So what you could say is, in terms of people remembering meaning, not style, they don't notice token changes, but they do notice type changes. Um, all right, let's use a silly example. Let's imagine that there's a series like Harry Potter comes to mind, where the actor who played Dumbledore in the first two or three movies, he actually unfortunately died, and they had to replace him with another actor. Or sometimes this happens on TV series when they get rid of one character and they replace that, a different actor plays the same character. Um, a lot of people didn't notice that the actor playing Dumbledore had changed because they switched, one white guy with a long white beard for another long, white guy with a long white beard. That was just a token change, and they didn't notice. Now, had they changed the type, so if all of a sudden Dumbledore had become a woman in, movies 4 through the end, then people would definitely notice because that is a much more categorical change, right? Not just a token change, that would be a type change. So that's just a silly example of the idea of token versus type changes. And using this terminology, what we can say is that people notice type changes and they tend not to notice token changes. All right. So now I'm going to contradict myself a little bit. I'm going to tell you about, excuse me, I'll tell you about this study from 2008 that was performed by Tim Brady, Talia Conkle, George Alvarez, and Ode Oliva at MIT. Um, and I just spent all this time telling you people don't notice token changes, they only notice type changes. And just to show you how complicated the field is, we're going to talk about this study because this study provides evidence that actually people might remember more details and have better memory for things than we would typically think. So what they did was they got a bunch of participants together and they viewed a whole bunch of objects. These are very nice photo pictures of objects. I'll show you some in a second. And people looked at these objects for about 3 seconds each for 2,500 objects. So that is a lot because you're only getting 20 objects a minute. So this took 5.5 hours. And during this time, people sat in front of a computer screen and they just watched passively as each of these objects was presented one after another after another. They took breaks about every 30 minutes or something. They did this all in an entire day. They brought pizza in, they try to keep people entertained and fed and all that sort of stuff. But it was still pretty grueling to sit there for just 5.5 hours and have images presented to you one after another. Then afterwards, people were shown 2 images on the screen, and they were asked to identify which was the image they studied earlier. So in the trade, we call this an old new recognition task because they have to say, is the image old or new? It's also called a 2 alternative forced choice task because you're shown 2 alternatives and you must choose between the 2 of them. So let me show you a couple of these images. So here's some pictures of what they look like. Let's zoom in a little bit. So let's imagine that you were shown the sweatpants in the training phase in that first 5.5 hours. So for 3 seconds, you saw this picture of the sweatpants. Then later in the test phase, your choice was between those sweatpants and this mason jar. And that would be a novel change, okay? So it's completely different type of object. Um, Now, the other case is in the middle here. This is an exemplar change. So these are all objects of the same type. They've just switched the exemplar. So imagine you studied the test tube on the left, and then in the test phase, you're given a choice between that test tube and another very similar looking test tube. Or you saw one of these chocolate cakes, and now you got to choose between which of these two chocolate cakes you saw in the training phase. Or you saw one of these pictures and you have to choose between two metal picture frames in the test phase. So that's an exemplar change. And the last one is a state change. So this presumably would be the hardest. You've got the same object in two different states. And they tried to pick states that were qualitatively different. So for instance, this abacus toy, all the beads are on the right or all the beads are kind of scattered. This piece of furniture, either the doors are open or closed. And then this one's a little hard to see, but you've got a cracked egg and either the yolk is intact on the right or the yolk is broken on the left. Okay, so that's a state change. Or it might have been, another example was a Starbucks coffee cup where the lid is on the coffee or the lid is taken off and set on the side, right? That's a state change. Okay, so people had to choose. They studied all these objects for 5.5 hours. Then later, they got shown two pictures at a time and they had to choose which was the one they had seen before. So the question I'm going to ask you is, thinking about these three different types, novel, exemplar, or state, pause the video, take a second, and make a prediction. What percent correct do you think people got for the novel comparison condition? What percent correct did you think people got for the exemplar? And how well do you think people could do at remembering these state changes? When you're choosing your percentages, remember that if you are blindfolded and you guessed randomly, you should get about 50% correct because there's two alternative forced choice, right? So 50% correct is chance. So how much better did they do? Okay, so hopefully you made your prediction. Um, and a lot of times students will say, okay, somewhere in the 90s for their novel, maybe in the 70s for exemplar, and then probably maybe in the 60s, like maybe a little bit above chance for the state change. That's typically how people guess. But here is the data. So people were 93% correct for the novel comparison, but they were 88% correct for the exemplar difference, which is incredible. And they were hardly any worse for the state change. They got 87% correct for whether they saw, for instance, a piece of bread inside the bread box or the piece of bread pulled out of the bread box. So to me, that's just incredible. I think these are just really incredible results. And you should note that these are not a fluke. This group has gone on and they did the same kind of protocol, the same kind of experiment, and they did it with natural scenes. So pictures of beaches and mountains and deserts and things like that. And they found basically the same pattern of performance. People were incredibly good at remembering exactly which objects they had seen before. So I spent the first part of this lecture telling you that we really don't notice token changes. We only notice type changes. And then now I'm telling you, well, actually, under certain circumstances, people's memory for pictures is incredibly good. And they're even aware of things like state changes, which is a very, very subtle sort of change. So just thought I'd muddy the waters there. There's some evidence that people are sometimes really good at remembering details. Oh, here's some of the actual, they had 14 people in their study. So this is how many people got these right. So, 14 out of 14 got the sweatpants versus the jar. 13 out of 14 got the test tubes. All 14 got the chocolate cake. That must have been a very memorable cake. The egg yolk, amazingly, 13 out of 14 people got that one correct. They remembered which version of that, of those two pictures they had seen. Okay, so let's start drilling in a little bit more and talking about what kind of representations that you have in your mind for storing all this stuff that you know. And some people have proposed the idea of a propositional network. And I was kind of describing that earlier when I was talking about the tiger versus the zebra, and that they're both related to the concept of stripes. And what we mean by a propositional network is that when people hear a message, they're pulling out the kind of propositional content of the message. A proposition is a statement that has some meaning. So the idea is that you don't remember exactly what the words were in the sentence. This is kind of going back to the mark carefully or versus carefully mark experiment we talked at the beginning. You're not really remembering the exact sentences. What you're remembering are the propositions, or sort of pieces of data that were communicated, the pieces of information that were communicated in that message. And so Bransford and Franks did a study, and we're going to simulate this study in a second. And they suggested that people encode information as propositions. So in other words, they're not just remembering the sentence, they're extracting the propositional content out of sentences. Then people relate those propositions to each other and build a network. And the idea is that people have a poor memory for exactly which propositions they heard and when. So let's try this. So here's some statements that Bransford and Franks used in their 1971 study. I'll present these to you, and just remember what these statements are saying. Okay, here we go. The ants ate the sweet jelly, which was on the table. The rock rolled down the mountain and crushed the tiny hut. The ants in the kitchen ate the jelly. The rock rolled down the mountain and crushed the hut beside the woods. The ants in the kitchen ate the jelly, which was on the table. The tiny hut was beside the woods. The jelly was sweet. And that's it for the propositions. So, propositions. So here's the idea. You hear all these utterances, and you're extracting the meaning. And so what might be the format of the extraction? So that first study was talking about the ants eating the jelly. The ants ate the jelly. How would we extract a proposition from that? The idea is you don't remember the sentence, the ants ate the jelly. It's more abstract than that. So if anybody has done any computer programming, you'll recognize this kind of syntax here. Basically, you have eat, which is your verb, and it's got an open parentheses and a closed parentheses, and that eating takes what are called arguments. So the arguments are the subject that's doing the eating, the object that's being eaten, and the time code, whether it's past, present, future. And so if I hear the ants ate the jelly, the idea is that I'm extracting a proposition in this form. I'm abstracting it away from the particular sentence, the ants ate the jelly, and instead I'm just encoding this proposition that something was eaten, it was eaten by ants, what was eaten was jelly, and it happened in the past. Likewise, jelly has the property of sweet. The jelly was on the table, and the ants were in the kitchen. All right, so this is the idea that these are the properties, the propositions that you would have abstracted from that first story. The second story, you would extract the propositions that a rock rolled down the mountain, that the rock crushed the hut, that the hut was beside the woods, and the hut had the property of tiny. So that's an example of how you might abstract away the information that was in those sentences. So now that I have distracted you for the last 60 seconds or so by talking about propositions, I'm going to give you a memory quiz. Which of the following did you hear? Did you hear the phrase, the ants in the kitchen ate the jelly? Did you hear the ants ate the sweet jelly? Or did you hear the ants ate the jelly beside the woods? All right. I think it's very clear that the third one is not correct. I was telling you propositional sentences, or telling you sentences, and they seem to switch back and forth between the two stories. One was about ants and jelly in the kitchen. The other was about the rock rolling down the hill. But we didn't conflate those, right? So the fact that you see a sentence that says the ants ate the jelly beside the woods, you know those are not related. They were two different stories. So we can rule that one out. The answer is you saw the first sentence, the ants in the kitchen ate the jelly, but you did not see the second sentence, the ants ate the sweet jelly. But the second sentence is pretty uh, possible, right? It's logical. People have a hard time rejecting the second sentence and saying that they did not actually hear that. So that's what we mean. That's kind of going back again to that first study we were talking about with the woman teaching the class and her changing her dress pattern. You're extracting propositions, and these propositions are related to each other, and that's really what you're getting. So you're not really remembering the details, you're remembering the propositions themselves. So for instance, if you're reading a book, you're reading a novel, characters are doing things, they're saying to each other, you're not remembering always the exact words they're saying, but you're remembering the meaning of the message, the propositions that are happening, not exactly how those propositions are communicated. All right, so let me flip back and make sure I covered, okay, here's all this stuff. All right, so people encode information as propositions, propositions are related, and people have poor memory for which proposition they actually heard. So the ants ate the sweet jelly, the ants in the kitchen ate the jelly, so there's your sentence. And it was you never said the ants ate the sweet jelly, but we did say the jelly was sweet, and we said that the ants ate the jelly in the kitchen, which was on the table. All right. Okay, next topic. What is the format of the information that you store in your propositional networks? Do you store it as abstract information, or is it tied to the perceptual modality in which you learn that information? And these two kinds of ideas have been proposed, and they're called by different names. So the first one is amodal symbol systems. And the word amodal is sort of interesting. By amodal, mode means sensory modality. So what did it, what sensory channel did something come in? Was it visual, auditory, tactile, etc.? So amodal is the idea that when you abstract information, you abstract it away from the particular modality in which you learned it. So if you read a book and you you kind of understand the story, the amodal says your understanding of the story is not just a verbal acoustic understanding, that you may also have visual imagery associated with it, or you may, in a more abstract format, remember the information without it being tied to vision or hearing, I guess, if it was an audiobook. On the other hand, perceptual symbol system says that when you learn information, it's encoded and it retains some characteristic of the sensory channel it came into your mind. So if you read a book, that's using your visual channel as opposed to listening to an audiobook. This would say that two different people one could read a book and the other could hear the book on an audiobook, and that their kind of propositional network of information would be slightly different because they got them through two different sensory channels. One was a visual sensory channel, one was an auditory sensory channel. And according to the perceptual symbol system, the idea is that you would remember these things. The person who read the book would remember it in a more visual way, like maybe the way that the words looked on the page. And the person who did the audio book would remember it in a more auditory way, like the way that the narrator's voice sounded when they talked about different events in the book. There's also the idea of dual code theory, which is that you are automatically generating both codes. So I think reading a novel is a great example of this. When you read a book, not only are you your eyes are going from word to word, and then that turns into an acoustic format, because as we mentioned about the phonological loop, even though you're reading visually, it has this phonological characteristic. You understand the way the words sound, even though you're not hearing them out loud. You also automatically generate visual imagery that goes along with the book. So you have a certain way that the characters look in your mind, a certain way, if they live in a castle, like Hogwarts, right? You got a mental image of what Hogwarts looks like. And that's kind of the idea of dual code theory, that you're recording both visual and auditory codes for these things. And that goes with that final thing here, which is that we may automatically be generating mental imagery of concepts as we understand and encode them. So when we talked about the visual imagery chapter, and I mentioned that there had been a longstanding debate in the mental imagery literature about the nature of the format of mental images. The debate was basically between people who are advocating for a modal symbol system, like these mental images are not actually visual, they're using some other part of your brain. And then other people who are saying, no, 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 when you make mental imagery, it's using the same part of your brains as when you have actual visual perception. And we looked at the study looking at the fusiform face area and the perihippocampal place area, and showing that, in fact, when you imagine faces and houses, it recruits the same brain areas as when you're actually seeing faces and houses, which goes more towards the perceptual symbol system side of the argument. All right, so there's your terminology: amodal symbol system, perceptual symbol system. Um, and truthfully, we probably have some of both. We're both remembering things in the format that we learned them, and we're also abstracting the information away into a format that's not tied to any particular sensory modality. Okay, so this brings us to another topic, which is the idea of embodied cognition. And this is an abstract topic. And let me see if I can introduce it in a kind of a weird way. The question of embodied cognition is the idea of what we call symbol grounding. Ultimately, how do you understand all the concepts that you have in your mind? So maybe one way to explain this is by telling a story. Um, there was this young boy. He was the son of a couple of professors at UCLA. This kid was smart. I mean, his parents were super smart. So when they got together and had a kid, the kid was really, really smart. And he was like 8 or 10 years old. And he had this kind of hobby. It's kind of a weird hobby, but he was a little bit of a smart, weird kid. He would open up a dictionary and he would just pick a word in the dictionary randomly. And if you look up a word in the dictionary, it is defined in terms of all kinds of other words, which are also in the dictionary, right? So you go pick up a word in the dictionary, it's defined in terms of other words, and then you could just go look up each of those other words in that same book, and they're defined in terms of other words, which then you could go look up in the dictionary, right? So the dictionary itself is this entire symbol system that is self-referential, but it doesn't connect to anything outside of it. There's no, it's like, ultimately, how do you have to understand language, I suppose. You have to have your own definitions of words in order to look up words and then understand them as being defined in terms of other words. So this kind of freaked him out. Like I said, he was a weird kid. He kind of had this existential crisis of sort of like, well, what is there meaning? If it's just words defined in terms of other words, like at some point, where do you get truth? Like, where does it actually get grounded in your experience? Well, embodied cognition takes that question of symbol grounding and offers an answer. It says, okay, ultimately, meaning at some, deep, 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 deep level, if we keep digging and going down, 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 ultimately, meaning is established through your bodily experiences of the world. So you understand that if I say, yeah, Tommy kicked Bobby, you understand the idea of kicked because when you hear the word kicked, you mentally kind of refer to or imagine the act of you yourself kicking something, like kicking a ball. Um, in other words, the word kicked has meaning to you because you have had a physical experience of kicking or being kicked that you can refer to. You internalize that in terms of your body, right? So well, this is very philosophical. This is very, very top level philosophy. But how do we ground our propositional networks, our semantic networks of knowledge? If they're just referencing each other, at some point there has to be meaning. There has to be meaning somewhere. And embodied cognition says that cognition, at least for some of the concepts, is grounded in your bodily actions and states. So I understand the word happy because I have been happy. I know what that feels like. I understand the word sad because I have been sad and I know that what that feels like. And so that forms a bedrock of meaning in terms of bodily experiences. And then you can build on top of that into more abstract concepts like justice and bravery. Those are not really, I guess you could experience somebody being brave, or you could experience some justice happening. But I'm trying to get at the idea that we can take simple concepts and then you can combine them into more and more complex concepts, which become less grounded in your bodily experience. But somewhere you got to have something where the symbols have meaning inherent. And the inherent meaning comes from your bodily experience, according to the theory of embodied cognition. Okay. Second of all, how is meaning communicated between people? So if I have an utterance like, oh, hey, there's free cookies in the lounge, um, you have to understand what I'm referring to and how that might influence your own behavior. And so, or maybe even better example would be, you say to somebody, how are you? And that person says, oh, I'm sad today. And you can say, oh, I'm sorry, what happened? And you're experiencing some empathy about that person. Well, one way to explain how this kind of idea of meaning is communicated between people is the idea of mirror neurons. So mirror neurons are in a part of the brain that is basically they were first discovered in monkeys, and the location of these neurons is in the language area of the brain, where what later developed in humans into the language area, right? So we call this a homologous area. It's not exactly the same. But mirror neurons are neurons that, so for instance, if the monkey reaches over and grabs an object, lots of neurons fire, but some neurons in this mirror neuron area fire. And then also if the monkey sees somebody else, another monkey or a human, grab that object, those neurons fire again. So in other words, those neurons fire when either the monkey performs an action or the monkey sees another person perform the same action. So what people assume is that this means that the mirror neurons represent the action itself. In the abstract, this is the important part. It's not monkey picking up an object and it's not human picking up an object. It's the object getting picked up in some way or another. So mirror neuron bridges the gap between understanding my own self and my own bodily experiences and seeing that other people have their own knowledge and bodily experiences. So if somebody tells me they're sad, I can appreciate the way that I can appreciate that is I have some mirror neurons in my brain that fire when I'm sad. They tell me they're sad. I can see it and those mirror neurons fire, and then that triggers my internal sympathy or my empathic reaction to their sadness. It's like I feel a little of their sadness too, and I feel bad for them. I want to try to comfort them. That's the idea of mirror neurons. And people get excited about these. We're going to talk about mirror neurons again later in the course. So I'm sure there's lots of people have questions who are just watching this video and you're not sure exactly what heck I'm talking about. We'll talk about it again. But the idea is that the neuron represents an act itself or a concept itself, regardless of whether the monkey does it or a human does it. And so that's kind of like a word, right? Like the word grab or pick up I guess that's two words, but okay, the word grab, it has meaning. I can grab something, you can grab something, and I need to understand that they both represent the concept of grabbing in the abstract. So for me to have a word like grab, I need to have a neuron that represents both you grabbing and me grabbing, right? There has to be some co-activation in both of those cases. So that's the idea of a mirror neuron. And it starts to get into this idea of multimodal versus amodal hypotheses, because these are definitely on the perceptual or the multimodal side. The idea that you understand knowledge is grounded in your bodily experiences, your visual, auditory, and motor experiences, and that's ultimately what's leading to your understanding of concepts. So that would be a multimodal hypothesis. All right, if you have questions about this stuff, write them down, shoot me an email, or whatever. Actually, that's a really good idea because I'm going to record the first lecture now, and I'll record the next lecture in a day or so, probably on Wednesday. So shoot me an email, and if you have questions about this stuff, and I will answer them at the beginning of the next video. All right. So let's start talking a little bit, and I think this will be our last slide. We'll talk about knowledge representations. So let's talk about the idea of a semantic network. It's very similar to a propositional network. The idea is that you know certain things. You know lots of facts about categories. So let's take a category like bird, for example. You know certain facts. Birds have wings. Birds have feathers. They fly. They lay eggs. They have nests. They live in trees. They sing, right? These are all facts that we know about the category of birds. And we could think of them as facts being related to, and categories being related by links. So imagine you have sort of a bubble that says bird, and then you have these other kind of bubbles near it that say flies, sings, makes nests, lives in trees, feathers, and all this other kind of stuff. And you have a link between the concept of bird. And when you think about a bird, it also activates all these related concepts. So Collins and Quillian came up with an idea where they thought of things in terms of a semantic distance effect. So here's the basic concept. If I have a node like bird, and I have all this stuff that's associated with bird, there's also the idea that a bird is an animal. And also dogs are animals and cats are animals, right? So animals have certain properties. They have, they have skin, they breathe, they're alive. And that's true for all animals. Well, if I have those concepts associated with the animal node, and then from that node, I have a pointer to bird, and then I know things about birds, like they have feathers, they sing, they live in trees, they fly. And I have a pointer from animal to cat, and I know they have fur, they purr, they meow. And dogs, they have fur, they bark, and etc. It would be really redundant if I encoded that they breathe, they have skin. That's all very redundant if I copy that information at every node, every subnode. So it's kind of like if I'm going to store information, it makes sense in terms of information compression to store information that's true for all animals at the animal node. And then I just have a pointer to examples of animals, and they inherit all of the properties of animal. And then at the node of those particular animals, like bird, I just store the information that's relevant for birds, okay? And this is really an information compression idea. It's like, why copy that information multiple places? You just have a node for that, just store it at the level of the hierarchy that you need. And then we can connect these things with links, which Collins and Quillian called ISA links. So for instance, a bird is an animal and a canary is a bird. And so when I make an ISA link, if something is something else, it inherits all the properties at that higher order node. So for people who are into programming, you can create classes, and then you can create kind of a parent-child relationship in those classes. And the child class inherits all the properties of the parent class. That's very, very similar concept, same idea. Um, so if you don't computer program and that made no sense, I'm sorry, but there's a couple people probably in the class who've done some programming, and for them that makes sense. So, for example, here's an idea. So we have, a person is capable of cooking, and cooking allows you to eat, right? So each of these nodes, they have these. So here's an is-a-link. A cake is a dessert, and a cheesecake is a dessert, and a cheesecake is a cake. All right. So you got all these kind of properties here, and a cake is used for eating. And eating has last sub-event swallow, right? The idea is that you've got some notion in your mind that all these things are related in this way. So Collins and Quillian proposed that there may be this sort of hierarchy to how these things are stored, that it would be efficient in our information, keep information that's true for all submembers of a class that are linked with is-a-links at the highest order node. So like animals have skin, they breathe, and that then you would have suborders like a bird is an animal and a canary is a bird. And so then they thought, okay, that would be a really sensible way to store the information. Is there any evidence, right? Can we find evidence in an experiment that that's true? And so what they did is they discovered something called the semantic distance effect. And it goes like this. I'm going to ask you to verify statements about things as either true or false. And I'm going to measure your response time to answer those questions. And the notion is, the farther you have to look through your network to answer a question, the longer it should take you to answer it. So what they did was they asked people questions. They said things like, does a bird have feathers? And people would say, true, bird does have feathers. Okay, and they would record the reaction time. Then they would ask a question, does a bird have skin? And it takes people, and they would again record their reaction time. It takes people longer to verify that a bird has skin or that a bird breathes than it does for them to verify that a bird sings or a bird has feathers. And so that they took as evidence that there really is this kind of hierarchy where things are, uh, facts are associated with the highest order node, the most abstract node. Um, and that if you have to query that node, so if I have to go from canary all the way up to bird, I can see, oh, feathers, that's very close. But if I have to go canary to bird to animal to verify that it has skin, then that's going to take me longer. And that's exactly what Collins and Quillian discovered. So that's the idea of semantic networks. Okay, the next topic is schemas. We're going to have a lot to say about that now, and then I will post it to YouTube and send out the link to the class. Again, if you have any questions about the content here from this first lecture, please shoot me an email and I will be sure to put the answers to this thing in in my next video. All right, class, thank you very much. Have a great day.